All right, today's lesson is on the integrated version of the rate law. What we've seen previous is what's known as a differential rate law. Now, the AP Chem test and most chemists refer to the differential rate law specifically as the rate law. So if they say rate law, they're deferring to the differential. All right, now there's a big difference between our differential rate law and our integrated rate law in that the rate law, the differential one that is the rate of change as the concentration changes. So here we were looking at how concentration is going to affect the rate. That's what we were doing back when we were looking at our differential rate laws. So you had data where they said you had a concentration and then you had the data that had the initial rates. So then you would have rates over here. Okay, that's how you know that you're going to do a differential rate law problem because you have concentrations versus rate data given. Now, because what we're looking at is we're looking at our concentration versus time, right? Because over time the concentrations are going to go down. Some concentrations go down in a linear form. Some concentrations over time aren't going to go down in a linear form. Some of them are going to go down more like an curve, okay? And another one might go in a more of a steeper kind of curve, okay? So these are essentially this would be zero, first, and second order reactions. Is we're looking at how does that concentration change over the time interval. Well, I'm not going to get into it here or into much because to be honest, I don't really remember much of the calculus, but I remember thinking it was really cool and it's really interesting. So if you have some calculus background, great. It could help you here a little bit. What we're going to do is we're going to take these differential rate laws, these rate laws here, we're going to do is we're going to integrate them, and we're going to come up with new equations. All we're going to do is we're going to look at how the results of the integration. I'm not going to do the integrations. I don't remember exactly how to do the integrals. I'm sure somebody could show me, but the point is that we're going to look at concentrations versus time. So if you have no calculus background, don't freak out. You don't need calculus to understand this either. It's just that that's the origins of all of this data. All right, so we're going to take these things, we're going to integrate. I'm going to show you each one. I'm going to show you first order. I'm sorry, that'd be zero order. I'm going to show you zero order, first order, and second order reactions. Okay? All right, so let's take a look at our first one, which is the first order reaction. All right, so for first order reactions, what we have is we've got essentially substance A being produced converting into products. We're just looking at a generic reaction here. Now the rate of change over time, right, that's what I was just showing you the graph of, we could say is equal to some sort of differential rate law. And that would be how concentration affects the overall rate. And that's what we looked at before. All right, we're going to take this and integrate it, and we end up with this form here. Now you might have seen this in a different format in your class. You might in calculus or in other classes you might have seen a little bit different, where you have like the natural log of AT over the natural log of what we've done is I've manipulated a little bit. This be negative KT. You might have actually even seen this as a natural. What is it to the E? I think it is. I think this might turn into a concentration over T, which is the concentration at time t initially is what we have, and you might have seen this as e to the minus kt. That might look familiar to you. That's the same equation. What I'm doing is I'm just manipulating this back into this format here. Okay, so this is my initial concentration. So this is the concentration at the beginning of the experiment. This is the concentration at the time I'm talking about, any particular point along the reaction. All right, K is the slope. T is the time that we're referring to in this, at the particular point in time in the reaction. All right, so if I have a reaction progressing, all right, I've got the reaction going down and it's curving like this. This would be time. This would be my concentration. Now, since I have a curve to this, well, that means that this isn't, this is the problem is in science we don't like curves. We want nice straight lines. So what we find is that if we take the data here, we convert this all to natural logs. And instead of plotting the concentration versus time, but I plot the natural log of the concentration versus time, what I'm going to end up getting is a nice straight line. And that's what I want. And this here is the slope-intercept form of that straight line. Okay, it's kind of a little trick we do in science. Is if we notice it has a curve to it, we try taking the natural log of it. And you'll see the other trick we're going to look at in a second. We're going to see this come up quite a bit, this little computation of taking the concentrations and converting them to natural logs. So y is my natural log at any particular point in time, so anywhere along this line here, this side of the graph. Slope is k. That's the same k that you have in your differential. It's black, you can't really see it, but that's the same k that you have in your differential rate law. No different. T is the point in time, so that would be where we cross over here. So that would be your x and your y, and then this would be your intercept at the initial. Okay, so I got a better graph of that on this next slide here. And you can see first order reactions, a plot of the natural log of the concentration of whatever we're talking about versus time. If it gives us a straight line, we can say that it's first order. And that's what we're doing here. So what the data is going to look like for you guys is you're going to have, well, actually, it won't even have it. You'll have concentration versus time. When they give you this data like this, concentrations versus time, you are going to use an integrated rate law. And that's the key here. Now I'll talk more about the specifics and how you're going to handle this in class. And keep in mind that you have a negative slope because that makes sense because as time goes on, your concentration diminishes, right? You lose your substance as it goes on. All right, so what you're going to do is you're going to take this, whatever the concentration is, convert all of these numbers into natural logs, plot it, and you get a straight line. If it is, first order. And then what you would do is you'd say, okay, my rate is equal to K A to the first power. So I'm going to write it like it were a differential rate law, and my integrated rate law would just be the natural log of A at point T minus KT plus natural log of A, and we're out of room here, but at initial, the equation that we saw in the last slide. All right, let's move on to the next type. The next type that you're going to see is a, oh, I forgot about the half-life. Half-life. All right. What we like to do with these types of reactions, we like to know, at halfway, oops, I say that again. At what time will half the amount of material be gone? Or how much will I have, how much time will I get half left over? All right, so it's kind of silly, but, it's just the way they do it. You use these a lot in radioactivity. Remember this in Honors Chem, we talked about radioactivity. So I'm not going to go through the derivation of this equation. If you want me to talk about it in class, I will, but this is the half-life equation. They don't really do much with this in the AP test, to be completely honest with you. A lot of these half-life problems you can figure out pretty soundly just by plugging into the equations, but yeah, I'm going to show it to you just in case you need to see it. But 0.693, it comes out when you do the overall manipulation of the equation. All right, that's what am I going to try to say? I'm kind of stumbling here, but the constant here is what's important. Notice that there's no concentration. Your half-life time doesn't depend on how much you start with. You could start with 100 grams or 1 gram. The amount of time it takes for 100 grams to cut in half and 1 gram to cut in half will be the same, is what this is basically telling us. It doesn't depend on how much you have. And that's really important for radioactive decay. All right, that's really where this used to come into play. They'd use this a lot in radioactive decay, but they dropped nuclear out of the AP test. So I doubt you're going to have to do anything with this, but we're going to go over some practice problems, and I'll talk a little bit more about it in class. Okay, and I'm going to show you the half-life equations for the other two orders as well. All right, so this is second-order reactions. Second-order reactions, again, notice they have the 2 up here, exponential change in our rates. So when we change the concentration, our rate changes at an exponential value. What we're going to do is after we integrate, our rate law here is going to give us this intercept form, right? It's going to give us 1 over. So instead of taking the natural log, we're going to do 1 over the concentration and 1 over the concentration here. We plot that versus time, we're going to get a straight line. Notice the difference here, positive slope, okay, so that would be m, okay? And here's the second order half-life equation. I honestly, I wouldn't lose sleep over this because I've never really seen them do anything with the second order. If they're going to do anything with half-life, it will be first order. Okay, and I'll talk again. I said I'll talk about that in class, so relax. All right, here's the equation. I'm sorry, the graph. So again, notice the difference here. The slope is going backwards. It seems to be increasing as time goes on. It doesn't make any sense, but don't forget, it's an inverse of the concentration. Okay, so again, if you have the concentration versus time, what you're going to do is you're going to plot this. If this doesn't give you a straight line, then you're going to plot the natural log of this. If that doesn't give you a straight line, then what you do is you do the inverse of this. If that gives you a straight line, then you know it's second order. If it's second order, you say the rate is equal to K to the second order, right? To the second power. That's another way of figuring out. So what I'm doing is I'm deriving this rate law and the effect of concentration on rate by using a second method, and this is using concentration versus time. It all depends on the data they give you on the AP test. Okay, zeroth order. Remember, zeroth order, this has no effect on the concentration, or I'm sorry, effect on the rate. So I can double this, triple this all I want. It has no effect on my rate. So therefore, it's just equal to a constant. So if I integrate this sucker, what I end up with, I did say sucker, sorry. Just make sure I was aware of what I just said there. Um, anyway, after integrating this, I end up with this regular, general, slope-intercept form. Nice and easy. Again, I wouldn't worry too much about this. I've never seen them do much with it. I always keep it in here just in case you want to use it, but I don't know. I'm probably going to start dropping it out since they're no longer doing much with Half-Life. But anyway, slope-intercept form, y and x. And again, we can look at the graph of this, and that graph comes out just like, so you do is plot your concentrations versus time. If that gives you a straight line, then you would say that it's zero order. All right? All right, so that's basically what we're doing. This, if you've noticed, you do a lot of graphing with integrated rate laws, and I'll talk about how you're going to do the graphing in class. But here's a nice little recap sheet of all the orders versus your various rate laws, integrated rate law. So here's your rate law, differential rate law. Here's your integrated rate law. Plot that you're going to use to get a straight line. Here's your slope, and then the half-life equations if you need them. If anything, this is the most important half-life equation to know. All right, last thing I want to do is just show you the difference between the two types of rate laws. Your differential rate law, which depends on concentrations and rate, so rate and concentration. Integrated rate law is concentration and time dependency. Okay, so that's the big difference. What the data they give you will dictate how you're going to solve these. Okay? All right, so that's it. I'll see you in class, and I'll make some more sense out of this. I'll see you later.